Hi everyone, welcome to our first video lesson. This first video is going to focus on 1.2, which is about measurement of segments and angles. So I'm just going to talk through some of your notes a little bit, and then we will try some practice problems together. So first of all, a figure or an object is distinct from its measure, and our notation must reflect that. So we need to be able to say what's the difference between an object's figure and an object's measure. So first of all, a figure is referring to the actual physical object. So here you'll see that we have line segment AB. So that's going to be that object's name. And here we have angle C. So that's how we name the object. However, you'll also notice that there are some numerical values that I have put in these pictures. The numerical value is referring to these objects' measure. So for instance, the measure of this object is 2. So we say AB equals 2. Notice that we do not put the line over AB when we are talking about measure. Measure for segments it could be anything. It could be meters, centimeters, feet. And the tool that we usually use to measure a segment is a ruler. For the angle, the measure is going to be 30 degrees. So we don't just put angle C, we put M, which stands for measure of angle C, is 30 degrees. And we know typically that angles are measured in degrees, but you're going to learn later on in your Algebra 2 career that there's something else we measure angles in, which is radians. And the tool that we use to measure is a protractor. So we have to be very careful, especially when we get into proofs later on, how we are naming objects versus how we are naming their measure. So just once again, naming a segment, we put the line over the top, telling it its value or its length, no line, and we tell what it's equal to. When we're naming an angle, we use our angle symbol. But if we're talking about the measure of the angle, we have to put an M in the front, and we'll tell it how many degrees it is. So here is a good way to kind of distinguish it using an example. So I've got this triangle PQR here. So I can think of this triangle as the union of 3 line segments. So I'm talking about the physical object. So if I union or combine and put together PQ, QR, and RP, that's talking about the actual object. However, triangle PQR also has side lengths. So when I'm telling how long each side is, PQ is 5, QR is 3, RP is 4, I do not put the line segment over the top of it. Now, when we're talking about angles, all geometric angles have a measure between 0 and 180 degrees. So just take note that when we're talking about its measure, we can write this inequality, but if we're just talking about x in general, we can also write this inequality. And notice that I do not have an equal to sign by 0, because you can't have a 0 degree angle. A 0 degree angle is really just a ray. What do I mean by that? Well, I can kind of use this as an example. Let's say that this angle was getting smaller and smaller and smaller. It's getting closer to 0 degrees. What ends up happening is you end up just getting the exact same line over the top, and it ends up just turning into a ray because it's closing, 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 and now there's nothing left. So no 0 degree angles. However, you can have an angle that's 180 degrees, and we're going to talk about that on the next page. So there are 4 different types of angles that we need to know in geometry, and you might actually know these already. The first one is an acute angle, which is any angle between 0 and 90 degrees. A right angle is when it's exactly 90 degrees. So notice that there's no lines under these inequality symbols because you cannot equal 0 and you cannot equal 90 if you are acute. Once you equal 90, you are a right angle. Anything between 90 and 180 is considered obtuse, so those are your wider angles. And here's where I was talking about before, an angle that is 180 degrees. So you end up getting a straight line. Okay, how is that different from the ray that we talked about earlier? Well, if you see this obtuse angle, if I was to open it, a straight line from one end to the other is 180 degrees. And there's the two arrows. Okay, it's not like the ray where it's one arrow. So an angle is going to be 180 degrees. So here's a new term, congruent. So this is the symbol for congruent. The equal part of the symbol means that two objects have the same size, and the squiggle on top, or the tilde as it's actually called, means that they have the same shape. So any two objects that have the same shape and the same size are said to be congruent. Now, objects are congruent, right? Two line segments can be congruent, but they're never going to be equal. And two measures are not going to be congruent, but they can be equal. So it's kind of similar to what we were talking about on the first page. So here are two examples right here. So two angles are congruent if they have equal measures. So I've got angle VAC and angle JHF, and we can write this, that they are congruent to each other. Or they also have the same measure, and that's what it means to be congruent. Same shape, same size. So they both have a size of 72 degrees. So we could write the measure of angle VAC is equal to the measure of angle JHF. So two differences going on here. When I'm talking about the object is congruent. When I'm talking about the measure, we put equal in between. Here are two wrong usages of the notation. So if I was to say use the object and put equal in between, objects can't be equal. Only numerical values can be equal, and measures can't be congruent. So basically I took these two and just swapped the symbols. So make sure that objects are congruent and measures are equal to each other. The same thing goes for segments. Two segments are congruent if they have the same length. So I have line segment BD and line segment RM. I could say that line segment BD is congruent to line segment RM because I'm talking about the object. But once I talk about its measure or its length, I take away the symbol on top and I say BD is equal to RM. And again, flip-flopping that would give you the wrong usage of the notation. So you just got to be very careful, especially when we get into proofs later, of how you are writing out your objects versus your measures. The last very important part of 1.2 is how do you mark that two things are congruent on a diagram? So you're going to be given a lot of diagrams that don't necessarily have measures in them. 9 times out of 10, when you're doing a proof, you're not going to be using the measures. You're going to be using the congruency between the pieces. So in order to show that two line segments are congruent to each other, we use hatch marks. So we just mark off, okay, I know BC is congruent to AB. They have the same length. So that's how we use the hatch marks. When we want to show that two angles are congruent, so if I want to show angle A is congruent to angle C, I use these arc-like marks to mark off that two angles are the same. So here are two more examples right here. I'm trying to show that DE and GH are the same by using two hatch marks, and DG and EF are the same by using the one hatch mark. How come I don't use one hatch mark for these two? It's because as you have more and more congruent sides, you just add more and more hatch marks. So if there was a third set of sides that were congruent, we would use 3 hatch marks to show that they're congruent. Same thing for angles. We use one arc measure to show that angle H and angle J are congruent, but to show that K and I are congruent, I use 2. If I was to use one all around, then that would mean all the angles are congruent. And right here, all I know is that opposite angles are congruent. So that's how we are going to mark it off in a diagram. So let's do some algebra embedded in geometric diagrams. So this is the first type, a system of 2 equations and 2 variables. So see if you can read through this problem and solve the first example. So I know that QRS is a straight angle and straight angles are 180 degrees. So I can take this measure of this angle, which is 6x plus 3y, and set it equal to 180. And that gave me my first equation. PRQ is a right angle, which is 90 degrees. So I can take this expression 4x minus y and set it equal to 90 to get my second equation. So now I have a system of equations going on. So you can use whatever method you choose. I'm going to use elimination. So I'm going to eliminate y by multiplying the top and the bottom equation by 3. Notice that I'm numbering my steps. Sometimes there's problems where you have a lot of steps. So make sure that you number them to keep it organized and so that I can follow it a little bit better as well. So I'm going to rewrite the first equation, keep it as it is, and the second equation becomes 12x minus 3y equals 270. I'm going to cancel out my y's and add straight down. So 8x equals 450. 18x equals 450, excuse me. And then divide both sides by 18. And I'll get that x is equal to 25. But remember, I need to solve for y as well. So pick either equation. I'm going to choose the second one. And I'm going to plug in for x to get y by itself. So this becomes 100. Subtract the 100 from both sides. Don't drop that negative by accident. And then divide everything by -1 and we get y is 100. So those were the two answers, x equals 25 and y equals 100. Okay, so here's our second type of equation. It could be a quadratic equation that you might have to solve in geometry. So see if you can try the second question on your own first. So in order to solve for x, I need to write an equation using all the pieces I am given. I am given that the entire large angle ABC is 112 degrees. I know that angle 1 is x squared minus 4x, and angle 2 is x squared plus 2x. If you think about it, this is the entire angle here, and 1 and 2, when you combine them together or add them up, make up the whole angle. So what I did is I took the expression for angle 1, added it to angle 2, and set it equal to the entire thing, which is 112. Now the rest is just algebra solving. So we're going to combine some like terms. So those are like terms. We'll get negative 2x here. I'm going to bring everything to one side so that I can factor to solve. But before I do that, I notice that everything is divisible by 2. So I'm going to divide out a 2 from everything. I don't need to leave the 2 because I'm not just factoring it. I'm eventually going to solve it. So if I divide this side by 2 and divide this side by 2, the 2's all go away over here and it goes away because 0 divided by 2 is 0. Now I just have to factor. So x and x in the front, two numbers that add to a -1 but multiply to a -56. So that would give me a -8 and a +7. And then I'm going to t-chart. So remember, you set both of your bubbles equal to 0 and solve, which ends up just being that you switch the signs. So we get -7 and a +8. But remember I said when you were solving quadratic, and there's a context, which there's a geometric context here, you have to plug your numbers back in to make sure that they make sense. So on the side, I decided to plug in 8, plug in -7, and make sure that it checked out. Here I got 32 degrees and 80 degrees, which does add up to 112. So this one checks. And here I get 77 degrees and 35 degrees. So this one checks as well. So you actually end up having two values for x in this problem. Last type is using congruence marks to create the equation. So given that the measure of angle A is 30x plus 6, and the measure of angle BCA is 60 minus 6x, see if you could find this outside angle, BCD. So this one right here. So notice in the diagram that the measure of angle A and the measure of angle BCA are congruent to each other because we have these congruence marks. So the first thing I probably would want to do is I would want to solve for x by setting the two equations equal to each other. So I'm going to combine some like terms. So I'll add the 6x to this side. I'll subtract the 6 from over here. And then if you divide, you end up getting that x is 1.5. But be careful. We're not trying to solve for x. We're trying to solve for this outside angle BCD, or an exterior angle, it's technically called. So what relationship could I use? Because I don't have an expression for BCD. Well, I do know that this angle here, angle BCA, and this one on the right, they form a straight line with each other, which means that they must add up to 180 degrees. So let's figure out what the measure of angle BCA is when we plug in 1.5 for x. So if you throw all of that in your calculator, you're going to get 51 degrees. So if BCA is 51 degrees, then the measure of angle BCD must be 180 minus that 51 degrees. So that ends up being 129 degrees. So I had to use the congruence marks to solve for x, and then use the fact that this is a straight angle in order to solve for angle BCD.